Welcome to PASCO, Exploring PASCO OpenSciEd Grade 6. How hard can you push something before it breaks? Starting with our anchoring phenomenon, cell phone damage. Americans break two smartphone screens every second. More than 50 million phone screens are cracked each year. An estimated 95 million phones were damaged in the world by dropping them. We spend 3.4 billion each year in replacing cracked screens, and that's not counting the 38% of smartphone owners who don't replace them at all. 27% of people said that their phone was in a case when they broke it. So think and share. Have you or someone you know ever broken a phone? What caused it to break? We'd really like to hear your experiences and share with our class or our webinar today. So, for sharing, I'd love if you were to post a short description of a time a phone broke on our Padlet. You can access this using your phone and a QR code. Additionally, there is a URL at the bottom that Heidi has posted into the chat. Thank you, Heidi. And just kind of share some phone breaking stories, whether that's your phone, student's phone. If you've taught students, you've probably seen a broken phone, often left that way for a long period of time. And so we love to hear your experiences. I see some people are already writing. Excellent. I posted mine just as an example. True story. I'm pretty negligent and drop things a lot, unfortunately. So I did drop my phone on asphalt face down and completely cracked the screen. Um, and I see we have other stories coming in. I'll give about 2 minutes here, let these stories filter in. All right, I see people typing. All right, looks like we got most of those. So let me bring this over to share. So I have mine, definitely, yep, dropped my phone, excited piranha, slipped out of my pocket onto a tile floor. Oh, that's good. The screen protector did its job. Spouse closed the car door on his phone. That's a new one. And I thought holding it in my mouth while I had a bunch of groceries in my hand was a good idea. Yes, I have definitely thought certain holds were better than they were. So there are a lot of different ways to break a phone. However, there's a lot of other things that break. In class, we want our students to think not just of broken phones, although those might be front of their mind. Those are important items to many students, but also in general, other collisions. So I'd also like to brainstorm some other collisions, and I'm going to give some more thought time on this. So because I would like to see 2 things. And I will also try to provide my own where I can think of one. So list a collision where objects were damaged during the collision on a red post. That's the first one. And then list a collision where objects were surprisingly not damaged on a green post. So where you thought this is going to be a problem, but it worked out great. On the post, make sure that you want to identify the objects that came into contact with each other during that collision and mark with an asterisk which object or objects were moving before the collision occurred. Again, I would love to see these on the Padlet, both where objects were damaged or where they were surprisingly not damaged. So let's say 3.5 minutes here. All right, you can also edit the color on those. I'm going ahead and just doing them because it's really quick for me. Let me bring this over so everyone can see it. All right, so we already have collisions where objects were damaged. Those are often easiest to think about. So a student broke a nail and a mask dropped on it. Ouch. Beaker was knocked off the table, fell into the floor. Two cars hit each other in an intersection. I was bouncing a ball, rolled it into a class, shattered it. Um, we've had some balls hit things but bounce off, such as a window. Two students running into each other. Yep, that's recess. Dropped a glass down the stairs, but it was carpeted. Oh, lucky for that glass. All right. Looks like we don't have anyone writing. So on to the next portion of this. So once your students have come up with a lot of different ideas, the next thing is let's start categorizing them. Let's start thinking, how do these collisions relate to each other? So are those examples that we thought about collision scenarios A, B, or C? A being the object was damaged that the object that was damaged or surprisingly not damaged was moving first and hit a stationary object. Situation B, the object that we care about was motionless at first, but was hit by a moving object. And C, both objects were moving before the collision. So there's no need to change a post or add anything new. But if you can edit, and I can also go in and edit these for anyone who's having trouble, just quickly edit and say, was your example a scenario A, scenario B, or scenario C? So I'm going to do mine, and I'm going to drag this over so people can see it. So this, I bounced a ball and it rolled and hit a glass. So that is stationary. So I'm going to edit that. So it is a type B. This one's scenario C, A. Great. This is also a C. A rubber ball hit a window but bounced off. This would be a type B because we care about the window. I didn't really expect the ball to break. And A. Okay. And then in class, you can start sorting these so students can see the different types of collisions. Go on, sort. Okay. Well, Padlet is, of course, this is how things work, right? When you're doing, oh, I have to drag to the top. There we go. All right. So now we can start sorting and seeing that even though we have different collision types, sometimes things were broken and sometimes things ended up miraculously safe, which probably leads us to start having some ideas about it. So we have our Padlet, what we're doing in a webinar, because we're not here in person, but in person with your students, you can expect to have a chart like this with your different collisions and all your different experiences spread out and organized based on type. And so you want your students starting to think about the different types of scenarios and different types of collisions. And so now that we have all these different collisions, we can start identifying common factors or patterns within these collisions. So students can start seeing that in all of these things, it's two or more objects have to touch. At least one of them is going to be moving in some direction towards the other. And every collision changes something. That could be the direction of the object that it's moving. It could be whether that object is currently intact or not. And then we can think about variables that affect whether or not damage was caused. And now we're ready to do a big step in the process, which is modeling. So we want to start modeling collisions looking at both time point 1, which is that moment right before the collision, right as the objects start to touch, and time point 2, which is the object just after those objects come into collision. So now would be a good time to reflect and think, take a moment and think about what students' models might look like, what you're looking for from them, and what you would hope to happen inside your classroom for this. So let's take a look at some student examples of consensus models. We have our first student, which is a car accident. Car accidents are pretty common. It wouldn't be unusual for a student to see one. And we can see some changes inside of it. This person, something about rearrangement of molecules as an advanced student. We also have our other examples, so say baseball bat and a baseball. So neither object was damaged, but maybe there's some movement going on inside. And then we have a really classic glass drops on the floor breaks. All of these models work because they hit on our key ideas. And then we combine these key ideas into a initial class consensus model. So inside our consensus model as a class, we expect students to realize that whether there's damage or no damage, these objects do have to touch. That's what a collision involves, two objects touching. And then there's some change, whether that's a change of direction or some sort of breakage. And maybe that's a permanent break, or maybe some objects might deform or bounce, but we're not really sure. And so we realize that while we have some basic models, we still have questions. And with those questions, we can start developing a driving question board. So this is where students start thinking of all the things they don't know about the model that they started to create, things that there's some uncertainty. And we can collect all these questions into what is called a driving question board. And so at the start, it's just a conglomeration of random questions, but the goal is working with students and then combine these into segments and different big ideas that we can start to test. So whether that's looking at the damage, what factors or variables affect that, how does timing affect this? Students might start learning about force and energy and how those things may be connected, and what determines breaking versus not breaking. Now, your segments might be different in your classroom, but these are just some general ideas you could sort them into. And now that we have all these questions, we need to start investigating them, right? The goal is to not just tell students how things are, but for them to start investigating for themselves. And we can see that we have some ideas that were collected as a class for how we might investigate these questions that we are not sure about. And so I very, very, very quickly walked you through the OpenSciEd instructional model, at least the first part. And so the goal here is to figure out instead of just learn about. So we started here at our anchoring phenomenon routine, and then we started learning about things. And then we realized, well, yes, we have a model, but we still have questions. So we created our driving question board. And then we were starting to navigate to with our ideas for investigation is, well, here's what we know, here's what we don't know. And now we're getting ready for my personal favorite part, which is the investigation routine, actually learning and discovering and performing experiments to find evidence. From there, you again put the question, you start putting pieces together, figuring out what we know, then go to figure out what we don't know, investigate, and so on and so forth until we have all of our questions answered. So we walked through the OpenSciEd version. So what is the certified PASCO version? Well, we can think about what hasn't changed and what has changed. What hasn't changed is it's still designed for NGSS and three-dimensional learning. It is storyline based instruction. Units are anchored by phenomenon, as we just went through, and lesson sequences are coherent from the student perspective and driven by their questions. Now, what has changed? PASCO technologies have been infused into investigations and demonstrations where appropriate. Physical equipment are provided in the PASCO equipment kits, and curriculum resources are organized and delivered in PASCO Portal. Now, you can find more information about this at pasco.com/OpenSciEd. And so I mentioned there at the end PASCO Portal. Well, what is PASCO Portal? So this is a place to host teacher resources in a digital environment so that it supports districts' IT requirements for both single sign-on access and distribution with learning management systems. It works with many of these common ones like ClassLink, Clever, Google Classroom, Canvas, Blackboard, Schoology. It hosts our core curriculum, such as OpenSciEd, the experiment library with a host of experiments and labs for different grade levels and different subjects, PASCO Academy, which is a multimedia resource. Additionally, there's professional learning opportunities, teacher support, and also software downloads for our sensor software and data collection. It was also voted Best of STEM for Best Digital Ecosystem for STEM Teachers for this year, which is nice to know. And again, more can be found at pasco.com/portal. Now, we know we have OpenSciEd resources. They're on the portal. What resources are provided for Unit 8.1 and where do we find them? So let me go to portal. Let me make sure it didn't log me out. Cool. So this is PASCO Portal. I'm logged in. You can see what I've been working on as my pinned and recently viewed resources. I will go to curriculum and OpenSciEd, go down to middle school and grade 8. We are in Unit 8.1. So this is Unit 8.1, Contact Forces. We start with a description and a picture for the unit. It lists all the next generation science standards that are covered within this unit. Additionally, there are some student files that you might want to share, posters, how students would engage in classroom discourse, and all the teacher files for this unit. I want to focus in on this really quick, which is the unit force overview materials. This is a really great way to get a, as it says, overview of this unit. Um, the most useful part here is this unit overview in storyline. So we'll jump to that. So unit overview just really quickly talks about what you expect to cover in this unit as well as the standards. And then the storyline jumps into a great overview of every single lesson. So you can see the storyline from really in a 1,000-foot view, get a good overhead view of everything that you expect your students to go for through this unit. I want to draw our attention. So, what I just did was an extremely accelerated lesson one. So, looking into lesson one, so our lesson resources, not just our unit resources, we have the question, what happens when two things hit each other, a description. There is also a student absence video, so you can send this to students in case they missed the opener for the unit. It's very hard to teach students when they're not even sure what we're learning about yet. We have our student files, which I'll get into in a moment, but I want to look at our teacher files. So pretty standard teacher files are slides. I have used many of these slides within this particular slideshow that I'm running right now. It's both in PDF, PowerPoint, and Google Slides format, so both editable and readily printable. Same thing, the teacher edition is our lesson plan. It comes with in Google Docs, Microsoft Word, and PDF as well. I will go ahead and open up the Google Doc. So we again start with our lesson question. There is no previous lesson, but this is where there'd be a quick summary so you can make sure you're navigating and knowing where you're coming from and where you're going. The current lesson as well as the next lesson description are listed. All of the standards that you're building towards are listed here as well. We have what students do and a really quick bullet point of what we expect students to figure out over the course of this lesson. Next up is the learning plan snapshot. This has a quick estimate of how much time it should take you for each segment, as well as a summary of each part, where you can find that in the slideshow, and what materials you're going to need to complete that segment. For a deeper look into the materials, there is the materials list. The materials list lists everything that you're going to need for this lesson, as well as the source where you will find it, how much you will need per student, per group, or per class. There's also what are you going to do with these materials if there's any preparation. You might have noticed there were a lot of charts that I just went through. So this recommends how you might build those charts for your classroom ahead of time. And then it gets into the nitty-gritty of each lesson part and what you want to say and how you're going to lead students through this learning experience. All right. So that's all of our resources and where you might find them. But I also mentioned, what about PASCO materials? Where are you going to source these? Well, first off, there's the Unit 8.1 Classroom Consumables Kit. These are all the materials that you would need that are going to be consumed. Post-its, index cards, rubber bands, things that you don't really expect to make it from one year to the next. They get used up. There's the Unit 8.1 Classroom Non-Consumables Kit. As the name suggests, we don't expect these to be consumed during a standard classroom experience, so you can use them year after year. And this is like your class set, like a class scale, or things, or often things that you're going to be using for demonstration. And the last one is the Unit 8.1 Lab Group Kit. So these are kits that are per lab group. So we expect every lab group to at some point need two PASCO smart carts, some bouncing balls. So this is what you would get for each lab group that you want your students to be in. Now that we have our lab group information of where we get our materials for our lab group, let's go back to what we last were talking about, which is testing our ideas for investigation. So inside of OpenSciEd, the first thing we end up doing is we go and take video or slow-mo of collisions. So using that lab group materials, we can start breaking things and getting close-up view of things breaking inside the classroom. We continue that to getting slow-mo videos of carts crashing into each other. We can see that the springs change shape but don't break. And you can see if you look very closely that the bumpers for these smart carts do deform a little bit, but again, no breakage. We get into things that we might consider non squishable, right? We don't really think of golf balls as being easily squeezed or changed form, but we can see in slow mo that when hit, they do. Additionally, this is a concrete part of a bridge that is getting crushed and it also changing. So even for objects that seem rigid, we learn that these do deform. And this is in lessons 2 and 3 of this unit. And so in lesson 4, we can say that we found that many things that appear to be rigid actually do deform, like this concrete beam. And so now we're ready to move on to our next step of investigation, which is starting to think, well, can we start breaking things of different sizes? Does that matter? Can we use different materials? As well as how much force is needed to break something. So we can start to quantify some of these videos and experiences we've looked at. Which brings us to the investigation from lesson 4, which is the material deformation lab. We'll look at the handout here in a second, but the investigation question is how much do you have to push any object to get it to deform temporarily or permanently? And for that, ooh, jumped ahead. And for that, we'll be using the PASCO wireless smart cart. You should be able to adjust on your screen if you'd like to see this bigger. There's a little slider there if you want to get a better close up of this. And so this the PASCO wireless smart cart. It measures both motion using the encoder in the wheels as well as the force here on our force sensor. It has two other sensors that we're not using today, which is the gyroscope and accelerometer, but there are other experiments that you might want to do inside your classroom with those. I'm going to go back to PASCO Portal and go to lesson 4, which is where this investigation is. You'll see that there's a teacher video for the materials. So you can start looking at the Spark View investigation and how you might demonstrate it. And these are the student files for this. So there is a reference for the investigation procedures. Notice that for all of these files, there are both English and Spanish, as well as Google Docs, Microsoft Word, and PDF, depending on how you'd like to distribute this to students. I'm going to open up the investigation and notice that it says first off that we should open a SparkView file. Where might you find that? That is additionally inside PASCO Portal, so I can download that and open it up. There is a student procedure as well, and there are some additional handouts that we're going to go into. I'm going to open up the handout deformation results. If you'd like to share this with students, you can just share this to Google Classroom, or if you're logged into your LMS or a single sign-on, there will be ways to send it to your students that way. But I'm just going to open up the Google document so we can look at it. First off, what object are we testing? Well, we are testing 3 wooden stirrers that are taped together. You can hopefully see it here. It's clear tape, but they're just taped together, nothing fancy. And we want students to look at what's our starting position, which is generally 0, how much force we're going to apply to the object, how much that object gets deformed or moved during the push, and did the object return to its original shape after. All right, so looking again at the investigation procedures, let's go ahead and open it up. I've already opened it up. Um, but next up, we'll connect our cart via Bluetooth. So I'm going to turn it on and quickly connect it via Bluetooth. All right, now that we're connected, we're almost ready to go. One thing, I'm going to make sure to zero it out. So it reads a small amount of force because it's very, very lightly touching on these just to make sure that there's no space in between them. So I'm going to zero this out and go ahead and start it. Note this is manual sampling, so I don't want to click the stop button. I want to hit manual when I'm ready to record data. So I'm going to record data at both 1, 2, 3, and 4 newtons, roughly. It doesn't need to be perfect. All right, there's my 1 newton. There's my 2 newtons. There's 3 newtons of force and 4 newtons of force. All right, so I can go ahead and stop. And even without doing much, we could see that's looking pretty linear. And so our next step for our students is starting to actually analyze data. They're in 8th grade, we're ready for graphs. So we're going to use SparkView to analyze our data and create a best fit line. So inside SparkView, I'm going to open up my toolbar and go to show hide linear fit, which will put a linear fit on this. It's pretty good. We got an R value of 0.999, which is excellent, and a slope of 8.43. Now, students are in 8th grade. They might, depending on your school, they may or may not be ready to be delving more into slope, but you can start talking about how, as the position increases, we are pushing with more force, which hopefully makes sense to them because they just physically did it. Now, this did have this as a demo for the teacher so that they could see how it's done, and now they can start testing their own things. So let's go ahead and do a different amount of stirrers with another run. So we can start looking at how do the trends in the graphs for different beam thickness or different materials compare. And I'd like to predict. So let us predict the shape of the new graph. Let me pull up the poll here. All right. So let's project the shape of the new graph with just one wooden stir. So will it be linear, but linear with a similar slope, linear with a different slope, or could it be curved, whether it's curved up or curved down? We have about 2 people, oh, 3, 4. We'll give a couple more seconds here for people to finish responding. All right, I'll go ahead and call it and share results. So it seems that of the people who responded, everyone felt that it was going to be linear, but with a slightly different slope. So let's take a look. So I'm going to zero it out again just because it had to move a little bit. Oh, let's get it nice and snug there. All right, I will zero it out. Start recording data. So even just slightly pushing on it, I can see it's bending a lot more. So I'm going to do those at every half Newton instead of every Newton just because there's only so far it'll go before it starts slipping out of out of the brackets. It's 2 newtons, roughly 2.5 newtons. Oh, 3. Oh, looks like we can't quite get to 3.5. See that it's bending a lot, and I don't know if you can hear it. I can vaguely hear it through my headphones. It's making a lot of creaking noises. Um, looks like it's about to be done here. Yep. Now we've snapped out. So I'll go ahead and stop, and we can see that we didn't quite get a line. If we try to put a linear fit to this, it's not a linear fit, unfortunately. We could even try using a different desired curve fit and try maybe a quadratic fit, which is pretty close. However, we can also specifically look at just the beginning portion. We can go and use this to toggle just to select. So I'm just going to select the first portion of it, where we can see it was quite linear in the very beginning, and it did have a different slope as everyone predicted. But once it started to crack, we no longer got a nice linear fit. Our data was no longer linear because the structure was changed. And so it's a good place for students to start thinking about that question on there, which was, did the object return to its original shape? So we can see that the three sticks are still very much in their original shape. However, the one wooden stirrer is now permanently bent. I would imagine even if I bent it back, we might not get the same forces out of it because we've probably permanently damaged some structures within it. All right. So that basically concludes that part of that investigation for students. Again, really quickly going through things, but to rehash, where can you find SparkView? So SparkView is a data collection software that I used for this investigation. It can be found within PASCO Portal under software help and downloads the license installer is included with PASCO Portal subscription. It is available on all of these operating systems and devices. And this was the file name that I downloaded for this particular investigation. And there are two different versions of SparkView. Both work the same. However, one is the native version of SparkView, but however, there's also a progressive web app that can be accessed through both Chrome and Edge. You can find out more at um, pasco.com/sparkview. And then Heidi put the link to the progressive web app in the chat. Thank you. All right. So every unit is structured. So unit 8.1 is structured into three lesson sets. Lesson set 1 is just how do objects interact, so the basics of collisions. Lesson set 2 is starting to look at how is energy related and how is energy related to the forces that they experience. And then lesson set 3 is the engineering task. So now how can we start designing materials to better protect objects during collisions? Through in this webinar, we just focused on lesson set 1. Lesson 1 being the anchoring phenomenon, getting through those questions and ideas for investigate. Lessons 2 and 3 were these slow-mo videos where students learned that regardless of how rigid an object might look, it still deforms, even if it doesn't break during a collision. And then lesson 4 was the investigation that we did together. Lesson 5 is a experiment in Newton's third law, seeing which object feels more force, or the fact that there's action reaction. They have equal and opposite forces on each other. And then lesson 6, like many other final lessons in lesson sets, is some sort of cumulative task or summative assessment, such as the transfer task that's found at the end of lesson 6. So at the end of lesson set 1, which is lesson 6, there is a summative assessment or transfer task. So students are asked to check their understanding on their own, some basic directions for that. However, you'll notice that it says here questions 6 and 7 will help us figure out where to go next. Do your very best to explain your reasoning. So even though it's a summative assessment for this lesson set, even at the end of it, we're looking forward. It's not just, do you know this? It's, well, what don't we know? What are we going to need to learn going forward so that it can lead us into lesson set 2? So this assessment is on soccer and headers and talking about injuries from these collisions and where might all of that injury be coming from? Is it more important that there is mass or speed within this collision? which then leads us to lesson set 2, which starts to talk about kinetic energy and how that affects the force. There is, of course, a assessment key for all of these assessments for better grading. However, this is not the only place for assessments. Yes, there are summative assessments at the end of every lesson set, but you can find the assessment system overview for a guide for what sort of assessments you can expect in each lesson, as well as a lesson by lesson assessment opportunities. So within each lesson, what sort of things are you looking for from students and making sure that you're eliciting the responses you want so that students are keeping up with the material. Additionally, within PASCO Portal, there is a grading planning tool. This is just a way to easily see what you're assessing each lesson, whether that's formative, pre or summative, whether or not it's going to go into the grade book, point value, and any notes. There are examples for how you might choose to do this. This is an editable document. So this part in purple was where this teacher decided that they wanted to add something to lesson 3, a CER based upon the experiment results. So just sort of you can always make it your own, and these are just some tools to help you guide you through the process. To additionally help guide you through the process, there is on-demand professional learning on PASCO Portal. There is curriculum training. These are PASCO. So this is just curriculum training and courses with certificates, both for middle and high school PASCO certified versions of OpenSciEd. There are videos to help walk you through different common processes, such as just navigating Portal, how to use SparkView, whether that's with middle or with high school. Additionally, there is professional learning for district adoptions. PASCO has partnered with Better Lesson to provide live virtual workshops, on site workshops, asynchronous courses, and follow up coaching. And these can be mix and match to whatever suits your district's needs. You can learn more about these and explore. If any of this interests you, we highly recommend that you contact your regional rep. You can find this at the QR code or at pasco.com/support. Additionally, there is a free trial to Pasco Portal. So whether you're interested in looking at the experiment library or what you can navigate through Portal, you can find this at pasco.com/portal-free-trial or at the QR code. Thank you, Heidi, for posting that in the chat. That concludes our webinar. Thank you so much for joining us.